Okay, AP Physics C, bit of an experiment here. I gotta get some more light maybe. I guess it's probably focusing on the board light, the exposure, so that's okay. I want to talk a little bit about this worksheet here, worksheet 2A. Just a little bit about how you get going on this one. So velocity versus time, right? On the worksheet 0 and on the quiz, we were finding the area under curved velocity versus time graphs to figure out the displacement. All right? The velocity versus time graph is one of the best graphs to have of an object to be able to know as much about its motion as possible. Really, you can learn a lot from any of the three kinematic graphs, but velocity versus time information is a little more direct, right? Because you literally have the velocity versus time posted, so you know how fast it's going everywhere. You can determine the acceleration by finding the slope of the line using a slopometer. You can know the distance it traveled, or its displacement, I should say, by finding the area under the curve over different time intervals. So this goes up at a pretty constant acceleration, so it increases constantly up until about 5 seconds, right? And about 5 seconds, it starts to, the velocity is still increasing, but it's just increasing at a lower rate until it approaches a constant velocity towards the end. So that's going to be your written description there. What is the max velocity of the buggy? How do you know? Well, literally just read it off the graph here. I'll leave that to you. Determine the distance traveled by the buggy over the following time intervals. 0 to 5, 5 to 10, 0 to 10. All right? So this is area under the curve. Now, for a triangle, this is pretty easy, right? Area under the curve, you can draw a triangle, right? This is kind of zone 1. We'll call this part up here, this is kind of like zone 2. 1 and 2. 5 to 10, 1 to 5, 5 to 10, right? So how do we calculate this? Well, from 0 to 5, we would just do 1/2 base times height. 1/2 of 5 times 2.5. The height here, be careful guys, you can't just count boxes always, right? You gotta watch out for the scale. So each vertical box is a 1/2 meter per second. I'll leave that calculation for you. Now, the curved region, how do we do that? Well, I like to count boxes, right? So we have, let's figure out how many little cubes are in here. So if you have a scale, have a grid, you can count boxes. And that's a pretty standard thing to have on an AP exam. Conceptually, the area under the curve is represented by the number of boxes there. Again, I know I'm kind of, the light isn't shining on me too well. I'll have to see about that. Maybe if I set up a light here. But we want to be able to see what's going on the screen anyway. So let's count boxes here. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28 full boxes. Now, so it's 28 boxes. And then we can count partial boxes. I'm going to erase the marker here just so I can see a little bit better. So I've counted for those 28. That's almost 29, right? That little one in the corner. And you know what? If I add that little part up there, that basically makes that 29. That's about, what, half a box? So maybe that's 30. Then maybe if I add that to this one, maybe that'll make 31. So I have basically 31 cubes, or boxes, I should say. So each of those boxes, right, draw a little box, is 1 second by 1/2 meter per second high, right? So each one of these represents 0.5 meters. So if I have 31 of these, each one of them is 0.5 meters, I'd have about 15.5, 16 meters for the displacement from 5 to 10. So we're literally counting boxes. And we typically only do things in 2 sig figs, so I'm just going to leave it like that. 0 to 10, we just add these two together. All All right, we just add those two together to get the total displacement over that time interval. Now let me just scroll down here. You guys can go back and take a look at that. All right, you scroll down here so you can see what's going on. It says determine the average acceleration of the buggy over these following time intervals. Average acceleration, average, it's the net change in velocity over time. Kind of like we had before, average velocity was a net displacement over time. Oh, these big markers, this thing's nice. I'm starting to get the hang of it. Shows up nice in the video too. It's the net change in velocity over time. Before we had constant acceleration, so we never really talked about average acceleration because they were always constant. Now they're not constant. We do have to consider average. So you look at the net change in velocity. Instantaneous acceleration at, right? That's the key word there. You find instantaneous values at a particular time. At 2 seconds, at 6 seconds. So instantaneous acceleration is the literal acceleration at a particular time. Now, for now, we don't have an equation for that. We don't have an equation for the acceleration at a particular time. We will shortly, right? And this worksheet's going to work through how to do that calculation, you know? So we said the average acceleration from 0 to 5 would be 2.5 meters per second. In 5 seconds, it's about 1/2 meter per second squared. Then I go from 2.5 to 3.5, so I only change by 1 meter per second over that last to 1/5 meter per second squared, our average accelerations. Now, to find the instantaneous acceleration, I forget the times I asked for. 2 and 6, all right? You have to determine the slope of the line tangent to the curve. Now, at 2 seconds, you know, I draw a tangent line, it's just going to be this 1/2 meter per second squared, the acceleration. But at 6 seconds, I have to draw a tangent line, right? So there's a few different ways to do this, and I'm just going to draw it pretty quickly. Did I do a good job? I'm not sure. I don't know. Not bad. I mean, I'm close to that point and that point, the tangent line. So the slope of the tangent line is up 1 meter in 1, 2, 3, 4 seconds. So at 6 seconds, the tangent line has a slope of about 0.25 meters per second squared, meters per second, right? Now, basically, to find the instantaneous acceleration, you could zoom in to the curve really close and pick 2 times that are really close to the curve. If you could really zoom in and get a really fine scale, as you zoomed in more and more, the curve would actually look like a straight line in your window. And then if you had a really fine scale, you could see. That's the essence of a derivative curve. It's still delta A over delta T, delta V over delta T, but you shrink that delta T down to an infinitesimally small change around the time of interest, and that'll give you an exact value or a close value of the acceleration at that time, right? You get an exact value if you manage to make that dt, that delta t in the bottom, approach 0. And that's a derivative. That's what a derivative does with a function, right? With a graph, you can't apply a derivative. The slopometer is your derivative, all right? Don't get hung up on derivatives and stuff. I keep introducing that vocabulary, derivatives and integrals, because it's going to be important very soon. And the more I talk about it, the better, right? So derivative is the slope of the tangent line. The integral is the area under the curve over a time interval, right? So we get an integral here, basically, a graphical integral. We get a graphical interval for the second half of the time as well, all right? So let's see. That's all I'm gonna say for now. Number two, you're gonna do that. We'll go over these in class a little bit better. I'm gonna write up solutions to these very soon. I've already written up all these solutions before. I just can't find where they are. I thought I scanned them and distributed them, but I don't know. I'll have to look back in my files again. But it could be my personal Gmail now I think about it. But take a look, do your best on these. Hopefully this video helps you get going, something you can refer back to on these basic definitions. All right, have a good one, guys. See you soon.